afternoon and welcome to today's last TOMRA Talks presentation. In plastic recycling, it's important to understand the complementary roles of mechanical and chemical methods in creating a circular economy. Earlier today, we covered the mechanical part with a presentation on advanced mechanical recycling. In this session, we welcome Dr. Norbert Niessner, Global Innovation Director at INEOS Styrolution, to cover the chemical part. He will talk us through the depolymerization process from yogurt cup to yogurt cup, the depolymerization of polystyrene, and the recycling performance of Styrenics, among other things. Norbert, stage is yours.
Thanks, Mitu. Thanks for the kind introduction. Hope you can hear me. Great. Yeah, let me introduce to you the chemical recycling, the depolymerization. We call it advanced recycling because indeed it's an advanced recycling method. Allow me just to introduce a few slides for those who don't know our company. So we are specialists, as the name says, in Styrenics, styrenic polymers, having, let's say, history in Bayer, in Lanxess, BASF, Nova, and so on. So we consider ourselves the #1 worldwide in Styrenics, and we have sites, production sites, R&D labs and offices basically in all regions of the world. And our major, or one of our major challenge, as with other companies as well, is to contribute significantly to improve the environment. And we see that in our role, we will do that together with our customers. So by addressing the topics littering and waste and carbon emissions, we want to prevent littering, reduce CO2, and to achieve this, develop solutions together with you, with our customers and partners along the whole value chain, and that's important. So it's not just quote unquote the direct customers, but we aim to work with all stakeholders along the value chain. And as we are members of Styrenics Circular Solutions, sitting in Brussels, we have day-to-day contact basically to all major stakeholders in this value chain. So our commitment to sustainability, just in short, is we want to save 1 million tons of CO2 equivalents in 2030, achieve net zero by 2050. We want to sell 500,000 tons of eco-products in 2030. And we want to guarantee 100% regulatory compliance, and we do guarantee regulatory compliance with conventional and eco-products, and therefore contribute to safety and the environment, which is equally important. We have, just very short, we are ranked now Platinum in EcoVadis. Some of you might know it. That's an important, let's say, acknowledgement of sustainability activities. And of course, we are intending to defend this position. I think we are top company here. Now, coming to the topic you were invited to today, and thanks Mitu again for having me here, because it comes from my heart to show you what we do in developing circularity pathways for Styrenics. So basically, we start with the feedstock. We produce the monomers, the building blocks, and one important monomer for Styrenics is styrene, of course. Then we do polymerize it in our plants, and our customers use the polymers. We, of course, aim and try to contribute as much as we can to stop landfill and stop incineration. So that is our aim. We want to do all that we can, and I think due to the unique value proposition of Styrenics, we can, to make it a whole circle. You see already half a circle, but the circle will be completed. So that polymers can be discarded in bins and recycled is known. Mechanical recycling is known to you as well. This is a typical pathway. You collect the stuff, you purify it to a certain extent, and then you make new polymers. If you do it, let's say, with great care, then you even can achieve the same quality as the so-called quote-unquote virgin polymer made out of fossil feedstock. There is another interesting technology, dissolution, Fraunhofer Creosote. You might have heard about that. For example, there are other dissolution technologies. We are looking into that as well. So that is an important, let's say, building block of the recycling technologies. And now today we are talking about depolymerization. And why about depolymerization? Because in the end, polystyrene is a unique material to depolymerize. It has a certain, let's say, feature given by nature that makes it easy, as we nerds say, to cleave the polymer chain into monomers, right? So PMMA, for example, plexiglass, you can cleave easily into monomers. Polystyrene, you can cleave easily into monomers. And some polycondensates like polyesters, you can also cleave easily into monomers. But not all polymers. So that is, we are happy, that we have polystyrene that can be converted from a long chain, polymer chain, into small building blocks. And that is called depolymerization. Beyond depolymerization, there are several other technologies like pyrolysis of mixed waste, gasification of mixed waste. We see that as an important part of our, let's say, of the whole industry's portfolio of recycling technologies as well. Because imagine you have a cheese packaging at home, right? It's a 10, 12 layer advanced high-tech packaging, actually. Nobody expects that, but it's true. Made of different polymers with different properties, like barrier against oxygen, against water, seal peel layer, and so on and so forth. How do you recycle it? You cannot delaminate it, and therefore, for such, let's say, polymers, or for such solutions, the pyrolysis and the gasification is, we believe, is a very good route. Yeah. And last but not least, of course, you can introduce natural feedstock. You don't need to use 100% fossil feedstock. More and more, the availability of non-fossil feedstock is taking place. So for example, in our eco grades based on bioattribution, we also use biofeedstock to be used in the steam crackers and then in our polymerization plants. So that is an additional option towards sustainability as well. Now a bit, let's say, technical stuff. So that's the polystyrene chain. Some of you might recognize it, and it is that with heat you can convert such a polystyrene chain into monomers. And as I said, this is a kind of a unique value proposition. There are just a few other polymers where this process works, like PMMA and polystyrene as well. The key is you need to achieve temperatures, let's say, beyond 350, up to 500, even partly 600 centigrades. Depends on the process, also different residence times, and then you can with a high technical yield achieve the depolymerization into styrene. You get also some byproducts, and you have to purify the styrene by conventional purification methods, and then you can use the styrene as if it was, from a fossil-based plant. Real, let's say, we knew what we are saying now. We knew for several decades, but in the context of recycling, we rediscovered polystyrene again, and we said, hey. You can collect it easily. That's a no-brainer. That's possible. With the help of TOMRA, actually, we co-developed sorting technologies, and actually TOMRA did it, that can easily distinguish between polystyrene, even between different polystyrene grades or polystyrene types, and other polymers. So here's really, I would say TOMRA is really in like the spider in the web. With this technology, that makes, let's say, sustainability work. And then, of course, you can apply different recycling methods, as I mentioned, mechanical dissolution, chemical recycling, and reuse the material. And our aim is, whatever we do, we are aiming to utmostly prevent downcycling. So just, let's say, the conventional recycling, as we all know from 20, 30 years ago, you have a product, you make then park benches out of it, and afterwards you discard it. This is, in our understanding, no recycling. We really aim for recycling and not downcycling, so that's important to mention. On top of that, we are aiming, together with partners like TOMRA, to keep the recycling quality so high that we even can use it for the highest possible standards like food and medical, and that is the ultimate, the ultimate proof in the end. That is what we are aiming to do. Chemical recycling is contributing to that, because in the end, at 500-600 centigrade, you create new styrene molecules, and of course you can use them as if they were coming from a fossil-based plant and repolymerize them into fresh polystyrene or ABS or other polymers, right? So that is our ambition, and by doing that, we want to, as I mentioned in the beginning, we want to contribute, selling these types of products in a large amount. So 500,000 tons in 2030, and we are on the, I would say, on the best way towards this target. Here you see an overview how depolymerization works. We call it advanced recycling because we really think that, let's say, using the term chemical recycling might not tell the whole truth. It's a really advanced recycling method that is still under development. It's already working, so there are plants in this world, operating. So that is shown, but we are working to improve that continuously. And with this advanced recycling, actually, 3 years ago, so at the last K Fair, we could demonstrate for the first time that yogurt cups made of conventional polystyrene can be substituted by yogurt cups made out of recycled polystyrene. And you see here our partner, that was Müllermilch. We had access to post-consumer waste, household waste actually, that was sorted with the help of TOMRA and also purified later on. And in the end, we ended up, I think, me too, with a 99.9% purity. That was amazing, actually. And with this pure material, we could make a depolymerization, create styrene oil that was distilled and worked up to styrene. And with that styrene, we went back into our polymerization plant, and made a polymer. So we could make, we call it recycled GPPS. Sorry for this, for these abbreviations. This means recycled general purpose polystyrene. So plain vanilla polystyrene made out of recycled monomers, and that we put into an extruder. We made a sheet out of polystyrene. We mixed it with high impact polystyrene in order to create some ductility, and then we thermoformed it and filled it. So we made this yogurt mit der Ecke, with help of our partner Müllermilch, based on recycled polystyrene. That raised a lot of attention at the last K Fair, and that shows that nothing is impossible. So even this highest standard of, let's say, food quality is now accessible via recycling methods. And both mechanical recycling, we heard that this morning, is contributing to this, but also depolymerization is contributing to this very ambitious target. Have to look at the time. I still have some time. I think one of the, let's say, key questions you might have, saying, hey Norbert, you can tell us a lot of stuff. Probably this is energy intensive, and you're creating additional efforts in purification and so on and so forth. We from the very beginning, we were collaborating with renowned institutes to calculate a cradle-to-gate LCA, basically, from depolymerization, but also comparing to mechanical recycling, comparing to the fossil-based route. So life cycle analysis, LCAs, we do from the very beginning. And let's say the learning out of that, and we have an animation here, is that you have a certain CO2 equivalent if you produce polystyrene in a conventional way. Recycled polystyrene actually saves you about 40% of emissions, and that's interesting. It's even more interesting if you consider, and we put it in as an extra negative bar here, if you consider the avoided incineration. Because what's the old route? The old route is you produce polystyrene the conventional way. You make a yogurt beaker, you eat your yogurt mit der Ecke or any other yogurt or whatever cream, and then you dispose it into your bin. And the bin is then, in the best way, it's collected. In the other way, let's say if it's household, it's incinerated, right? And the incineration creates additional CO2. And if you calculate the CO2 and calculate that you avoid the production of this CO2 by incineration because of the recycling path, then you add another incentive, and you end up with minus 82%. And that's, in my opinion, the true calculation, the true effect of recycling, in this case depolymerization recycling, for our mother nature. And I think this is remarkable. So I'm still excited about that. I know that now for many years, but I think this is we did not expect that, actually. So it's so we really do something good for our planet. And so depends on, as I said, some LCAs calculate with this negative bar, some without. But the bottom line of today's talk is we do something remarkable for our mother nature with respect to CO2 avoiding. And we are at the beginning. I mean, we are on the steep curve of the learning curve. You all know the concept of learning curve, right? So once you start with a project, you haven't reached the climax. You start and you learn every year. And that's what we do. We still learn every year. We have R&D colleagues. I see Michiel in the background. He's our R&D guy. They are working on improvements, and you can count on it. We are striving for further improvements, and this is a momentum screenshot or snapshot, and it will, let's say, the situation with more development will further increase, and I'm pretty sure that in the future we can report further, let's say, progress even in this field. We are working already for a few years. So I think this is let's say the conclusion here. I mentioned the 40% minimum greenhouse gas reduction and the 82% including avoided incineration. But the point is that with polystyrene you can do it. And that's why we believe this material. I mean, we are producing it. You would say, hey, Norbert, you have to say it. You're kind of an R&D sales guy. Yes, I am. But one thing is true as well. This unique value proposition you cannot buy. You either have it or not. And with polystyrene, you have one of the few grades of polymer where you can do this depolymerization to a great extent, in a high yield, not 100%, for sure not, but to a high extent, and we are working on improving the yield year by year by year. So that's basically what I'm going to tell you. We have, this is a bit, let's say, taking reference to what I meant before, the eco grade. So we are not only looking into depolymerization, we are also looking, as you have seen in one of the slides, into bioattribution. So we are buying monomers from the market, being produced not from fossil feedstock, but from biofeedstock. And by by certification, by official certification procedures, we can allocate this biocarbon to our product. So this is another important, let's say, pillar of our eco strategy. And here, basically, second last slide, just want to show you we have an overwhelming amount of so-called eco grades, and we are over and over increasing that. Yeah, so that is basically the message for all industries, all relevant industries that we are serving, from automotive via electronics, household, over to construction, healthcare, packaging, toys, sports and leisure. So that is the outlook. We are working in a time scale of, let's say, a little bit than 2 more years, where we believe that we will have achieved also on a commercial scale all our targets. So some of our projects are in the R&D phase, are in the pilot phase, and you might know some of our announcements. We regularly announce via press releases where we stand. But in this timeline, in order to fulfill our 2030 targets, we believe that in a bit more than 2 years we will have achieved the major targets, and we are already on a good way. So I can say, visit our stand, our booth in hall number 6, and you can see by yourself. That is the true last page. I would say thank you to you for attending this meeting. Ask questions. I do my best to answer it. At this stage, I want to say thank you to Jürgen Priesters from TOMRA, Senior Vice President TOMRA, who helped us in writing this book, Recycling of Plastics, which is just published. So go to the Hansa booth at the entry north. And Jürgen is contributing, of course, the TOMRA chapter on sorting. And I think together with him and other co-authors, it's a great book. Please help yourself. Look at the look at the Hansa stand and have an own impression. And that shows that in this industry, in the end, it's a small world. So we all have to. We want to collaborate. It's not a linear relationship either. It's circular economy, but it's also a collaboration along the value chain, as I meant in my introduction. And I'm so happy, to work with persons like me too, with persons like Jürgen Priesters and other colleagues in sorting, with persons from from Remondis, from university, so all over the whole value chain, in order to make really this recycling happening. Yeah. So that's basically all I would like to say today. Thank you very much for your attention. Any question, please let me know. Thanks.
Good. Thank you, Norbert. Jürgen is at a panel discussion, as you know, so we'll pass along your thanks to him when he returns. With that, I'd like to open the floor to questions.
Good afternoon.
Hi.
You show us one example for using the recycled material for food application.
Right.
This is as example, or there is a lot of companies that are using the recycled material for food content?
This both is true. I think you can hear me, right? Okay. So I hope you still can hear me. Yeah. No, both. I think both is true. There are several companies working on food grade recycling, be it chemical or be it mechanical recycling. So that's an activity of a lot of industries. And as you might know, with PET, I think PET were on the forefront of this development. If I remember correctly, they were the first to report a method, a technical method, a recycling method with degassing of low molecular weight substances and so on, to convert recycled material into food quality recycled material. And if I may stay on a bit nerdy level now, the key is the glass transition temperature of the polymer. So if you have a glass transition temperature that is below room temperature, then the chains are so mobile that you cannot freeze the cats and dogs, the ingredients, into the polymer, so they will migrate out. So bad luck. Yeah. Luckily, PET, same as polystyrene, have a high glass transition temperature, so above 70, 80. In polystyrene, it's 100 centigrades. That means polystyrene is a glass. And whenever you have cats and dogs that could, so the co-monomers or some impurities that could migrate out of this recycled material, they are trapped actually in this glass, and the glass retains them, not complete, not 100%, but to an extent where the, let's say, the analytics, the official analytics say, wow, yeah, it's what we detect is fulfills food quality. And that's what I mean with UVP. You need these types of polymers, so you're right. Others are working on that, and PET is successful. We are successful. Other polymers which have different, let's say, physical properties might have a challenge here. So that is kind of a, I would say, it's a well, you can call it windfall profit of Styrenics. We didn't create the glass transition temperature. It's there, but we use it for the benefit of recycled food grades. Yeah.
Thank you for a wonderful speech. And I have a question that is what's the difference between chemical recycling and advanced recycling?
Yeah, we it's actually, thanks for the question, and sorry that I probably did not point that out correctly. We believe that in the communication, very often chemical has a negative connotation. Although there's nothing wrong with chemical. I mean, we are working in chemical industry and we are proud. We are proud of being chemical industry. But what we see is that chemical depolymerization is indeed an advanced recycling method. So we said, hey, why not doing good things and talk about it? So it's basically, you can call it the same. So we call, let's say, advanced mechanical recycling, so to food grade, and depolymerization, we subsumize it under advanced recycling. It's just our choice, our personal choice as company, but it's part, so the chemical depolymerization is part of this advanced recycling. Yeah. But thanks for making me aware. I should have pointed out that stuff clearer. Yeah, thank you.
One question. You show the potential of PS really becoming the next food-to-food material. What do you see of the timelines for that kind of really penetrating the market and being the next PET?
The next PET.
Or kind of having that same, that's a material where we're really kind of close the loop. How do you see the timeline for that?
I mean, let's be honest. It will. We are never aiming for creating polystyrene as the next as a next PET, simply because the applications are different, right? So PET is a transparent material, excellent for bottles. So that is let's say a super application for PET. Our polystyrene typically is an opaque material. You know, yogurt beakers, it's opaque. Therefore, we have different applications. But what we see is that, especially in dairy product industry, we have a lot of advantages. And again, this is partly windfall profit. It is as it is. It is this nice glassy behavior that traps impurities and not prevents, but retards the migration, the unwanted migration. That's a great advantage. The other thing is simple as well. Yeah, that's why people like polystyrene in dairy industry. You can easily process it. So the energy consumption in processing and thermoforming is significantly lower compared to partly crystalline materials, like PET or PP, for example. Then we have this excellent sortability. So we have learned that from TOMRA, that you can distinguish even between general purpose, half impact and full impact polystyrene by near infrared technology, right? And all that together makes actually polystyrene, in our opinion, the material of choice for this type of industry. But we will, of course, never enter the bottle industry because simply the product properties are different. It does not, in our opinion, to the best what we know, not fit into that industry. So it's, I think, excellent question, by the way, but I think we will go our way, let's say strengthen our position in the traditional markets, by our unique value propositions.
My question is about chemical recycling. Have you heard about the technology with microwave
Yes.
instead of pyrolysis?
Yes, yes. This is a company called Pyrowave. It's a Canadian startup.
Yeah, exactly.
Yeah, I know. And it's, in my opinion, a very smart technology. So if I understood that right, and they have also patented it, and we of course have read it, they are applying microwave to the recycled material, which is in a let's say in a reactor, right? And as far as I understood, the microwave radiation helps to heat up locally the temperature so that the material decomposes. So that means with that technology you can introduce heat very rapidly into a big mass with A, not with E, into a big mass of polystyrene. And that sounds simple or trivial, but it is not, as it is a thermal insulator. It's a challenge to the engineer to introduce heat, and they did it by microwave. I think that's a pretty smart technology, and I think they are working in the moment on projects. I think they have announced a project with Michelin in France.
Yeah.
I cannot judge, let's say the whole potential of that, but I truly believe this is a smart approach, helping, bringing another aspect into the recycling discussion, and it is a kind of a chemical recycling supported by microwave, right?
Depolymerization.
Depolymerisation, exactly.
Okay.
Yeah.
Thank you.
Yeah.
With that, I thank you for coming.
Thank you,
and
me
being
too.
part of TOMRA Talks.